Hello everyone. In this session, we are going to see nucleophilicity of the acyl derivatives. So, firstly, already we know that acyl derivatives are nothing but the carbonyl compounds and the certain living groups or the nucleophile. We can say that. So, these are the derivatives generated by the carbonyl groups actually, or the carbonyl compounds. And what is meant by nucleophilicity? It is nothing but the nucleophilic substitution reaction in which we have the incoming nucleophile and we should have the living group that has to be substituted in the carbonyl compound. Okay, so firstly, nucleophilic acyl substitution is nothing but the type of the substitution reaction involving an acyl group and a nucleophile. So in nucleophilic acyl substitution, the nucleophile displaces the living group already, we know that, which results in the another carbonyl compound. So it is beneficial or it is useful to produce or synthesize a number of acyl derivatives having the different living groups or the nucleophiles. So resulting product in the nucleophilic acyl substitution is the carbonyl compound with nucleophile. So it can react with various nucleophiles. Thus, nucleophilic acyl substitution synthesizes many products. Okay, so before exactly the product or the reaction, we should know the what are the steps involved in the mechanism. So first step is nothing but the attack of the incoming nucleophile, which will provide a tetrahedral alkoxide intermediate. Alkoxide already we know that the compound in which a negative ion present on the oxygen atom. Okay, and in the second step, whatever the nucleophile and the intermediate we have that has ability to expel that leading group that present in the carbonyl compound. So with the help of that removal of leaving group, we can get the respective acyl derivative. Okay, so it can be seen from this mechanism in which first step, whereas the incoming nucleophile attack on the carbonyl carbon because it is electrophilic one. So there is a transfer of the double bond in form of the negative ion, a negative charge on the oxygen. So there is the intermediate formation, which is nothing but the tetrahedral alkoxide intermediate. And again, in order to remove the leaving group, the negative charge again participate in the compound, or we can say that in form of the resonance to make the compound more stable to get the product. So lastly, we are obtaining respective nucleophilic substituted, what we say that acyl derivative. Okay, so generally, the nucleophilic acyl substitution is totally based on the nature of the leaving group and the incoming nucleophile. So the condition is that incoming nucleophile should be more basic than the leaving group. Okay, so this nucleophile, whatever the nucleophile we are dealing with, that nucleophile should have the higher basic nature as compared to this living group. This is the condition only. And on that basis, we will what we say that see a trend in the nucleophilic substitution. Okay, so living group has the ability to detach itself from the acyl compound, and whatever the living groups we have, they should have the less basicity. Okay, if they have the less basicity, they are good living groups. While if the strong basis, the living group has the strong basicity, then they are poor living groups. So generally, strong bases are poor living groups. For example, we have the HCl and acetic acid. Okay, so HCl is a stronger acid, while the acetic acid is a weak acid. So there are conjugated pairs. For example, HCl is a conjugate acid, stronger one. So its conjugate base is a weaker, while the acetic acid is a weaker acid, so it's stronger. What is that? The conjugate pair, that is conjugate base, is a stronger. So we can say that chloride having the less basicity are better leaving groups as compared to the acetate in concern with the basicity. So the chloride has the less basicity nature, so that's why they are what is the good leaving group. So Finally, we can say that whatever the basicity associated with the living group is the main or the key factor in concern with the reactivity of the nucleophilic substitution. So, the reactivity of acyl compound increases with a decrease in basicity of living groups. So, these are the types of the acyl derivatives in which acyl halides, anhydride, esters, amide, and carboxylate ions. So, they have the respective living groups. For example, acid chloride living group is chlorine. Anhydrides, we have in which they have the respective living group. Esters or carboxy group, there. Amine is there. Okay, so they have the different living groups, that is nucleophiles. We can say that, and so it will leads to respective acyl derivative. Okay, and they have the actual certain trends in concern with the reactivity of the nucleophilic substitution. So chloride, that is acyl chloride, shows the maximum or a higher rate of the nucleophilic substitution as compared to other derivatives. Why? Because chlorine is the good living group, and if living group has the better ability to detach itself from the carbonyl compound, then it will show the higher rate for the nucleophilic substitution. This is the only reason. So that's why acyl chlorides are the more what we say that uh, they have the higher rate of the nucleophilic substitution as compared to the anhydride, ester, amide, or carboxylate ion. Okay, so this is the these are several facts about what is it, the reactivity trends for the nucleophilic substitution reactions within acyl derivatives. Okay, thank you.